Good morning. Good morning.
Good morning, Professor Cruz.
How you doing, Chantel?
I'm good, and you? Good morning, Tori.
Pretty good.
Good
Pretty good.
morning.
Hi, Tori. So we're looking at our test tomorrow. We've had a little bit extra time, maybe a day and a half extra to get this in. But generally, this is the toughest material. So we'll also have a little bit more for the last chapter too. About the same amount of time as this. So after today, we have. So just to note, and like I said, I only say this because I get these emails from the dean saying to let everybody know last day to drop is next Monday, and I think it's before 1 o'clock, so before the class starts. I don't think anybody needs to do that that's here. I know they don't. So I'm just, but the dean for some reason likes us to let that out. I think there's a lot of students that don't know how to drop, and the ones that don't come, I think they just don't understand what effects it has. So it's always best just to put in your best and hopefully everything will come out all right. So, has anybody got anything specific that we want to look at or want to poke around in that review?
I'm good with doing the review.
What's that, Tori?
I'm ready to start on the review.
Okay, good. The thing about the actual homeworks, the Newton daily stuff, is that you get 3 of everything, kind of. So it took quite a while to go through that. So here we go. All right, let's see. All right, so this one is just kind of theoretical, but it's talking about 5% of adults participate in at least 30 minutes of exercise each day. How likely is it that a randomly chosen adult will exercise 30 minutes a day? In other words, if 5% of the population are exercisers, then how does that figure probability wise? Is that a lot? In other words, is that very likely? Is that close to 100 to 1 or 1 to 100%? 5%'s on the other side. So it's not zero, but it is close to zero. Okay. 5% is usually what we consider, or anything less than 5% is usually what we consider a rare event. So there are a lot of things like that you might not think about. Like math teachers, especially like math on our level where we have a master's degree to teach the first 2 years of college. That's a very rare commodity to have. I mean, I'm not, saying there's something special about me, but activity about as far as probability is concerned, there's not really very many people that do that percentage wise. It's probably in the same category as the 5% of people who exercise. So does that make sense?
Yeah, I
Start at
mean,
0%, one,
right.
2, 3, 4, 5, and then keeps on going up to 1 or 100%.
Okay.
So what did you say, Tori?
I just I don't know, I kind of guessed, but I got it right.
Yeah, because it's very
It's
close to
point
zero.
zero five,
5%,
right?
0.05. Yeah.
Okay.
All right. Diana is packing a lunch that will include an orange. Diana has 3 navel oranges, 5 mandarin oranges, and 4 Valencia oranges. If Diana selects an orange at random, what is the probability that she selects a navel orange? Well, it's just the same kind of thing. Total oranges is 3 plus 5 plus 4. So that's 12, right?
Yeah.
So that's going to be our denominator. Our numerator is what we're looking for, the event, which is a navel orange. So probability of a navel (3 over 12). And then both of these are divisible by 3. And it wants simplified fraction, so that's what we're going to put in. All right. Does that make sense?
Yep.
The probability that Lou is on time for a given class is 75%. So 0.75 probability wise. If there are 32 classes during the semester, what is the best estimate of the number of times out of 32 that Lou is on time to class? So it's just a multiplication problem. .75 times 32. And what's that going to be? It's 20 something. And there's a phenomenon that's going to happen here when we do a thing for 32 times point. Actually, it's right at 24. Because if it were like 25.2 or what, anytime you're dealing with like the size of a sample, which is kind of what this is, you got to have a whole number. So you don't count partials. So in this case, we didn't have to worry about it, though, because it's came out even. All right, so if the probability of a cat owning family is 0.10, 10%, the probability of owning a dog is 0.2 or 20%. The probability of owning a cat and a dog is 0.8. What is the probability of owning both? I'm sorry, owning a cat or a dog. Here's the key. Okay, we don't know that. Cat or dog. So what we're doing is we're using our formula for or. C or D is equal to probability of C plus the probability of D minus the probability of both. Okay. All right. So then what's going to be on each of those? I'll write it up at the top. We don't know this one because they're asking for that. So it's basically number crunching. We're going to fill in each one of these. So this one's going to be 0.1010, and then the dog is 0.20, and then the probability of both. All right. So that's 0.3. I think it's 2. Let me double check it. And that is correct. 0.22. Okay. A child has toy blocks that contain the numbers 1 through 80. What is the probability that the child will pick a number that is not a multiple 11? So the easiest way to do this is just to find, first of all, the probability of a multiple of 11. All right, and we only got to go up to 80. So we got 11, 22, 33, 44, 55, 66, 77, and that would be it. That's all the ones that are 1 through 80 that are multiple of 11. So therefore, the probability one, two, three, 4, 5, 6, 7, 7 over 80, correct? All right, but that's not what we want. We want the probability of not a multiple of 11, but we didn't do anything unnecessary because we're just going to use the complement rule. In this case, I will push my belief that using the complement rule is the easiest way to go because it's not going to be so easy counting how many are not. Because the easier way is to find out how many are and then use the complement rule. So my assertion then is the probability of not multiple of 11 is equal to what?
Is it
7
80
from
minus
8 is
7?
1. Oh, I'm sorry. It's 80. There we go. So it's 73 over 80. I just about messed that up. All right. So Chantel, you see how to do that? I think we talked about that yesterday a couple of times. You can use the this is the complement rule, but this is the easier way to do it. If you've got the probability of yes, then you can find the probability of no by just taking subtracting it from 80, and that gives
Okay.
you 73.
All right.
And you're going to do the same thing with the complement rule. It's just that it's just that doing it the way with finding the common denominator, it just makes it more complicated than need be. The
Okay.
short and simple of it is to find the complement, you subtract the numerator from the denominator, and that will become your new numerator for the complement. And then you can bring over the same denominator.
Which is 80. Okay. Thank you.
Okay, if A and P are independent, then what is the probability of P and B? This can't be any easier for this. There's no, when they're independent events, you just multiply them. Even if they're dependent events, you still multiply them. It's just that you would have a different B there. So probability of A and B is equal to 0.1 times 0.8 I think that's 0.08. Let me check. One times 0.8. Yep, 0.08. 2 decimal places, and we got that. And you got to watch it. Zeros and such. There's an extra 0 in there. Let's look at this. This is one of those that's kind of a pain in the neck. I remember doing this before. All right, so we're going to have a Venn diagram. Each of the dots outside the circle represents a voter in a swing state. In this experiment, 6 voters are asked whether they support certain issues. 3 of the voters are registered Republicans, represented by red dots and labeled 1, 2, 3. 3 of the voters are registered Democrats and are represented by blue dots 1, 2, 3. All right. The events in the event diagram are support of a farm bill, supporting new budget. All right, voters 1, 2, so it's farm bill and budget. You can do both. So voters 1, 2, 3, and D1 support the farm bill. All right, so all of these are going to be in here. We're going to find out where they're going to be in a second. And then D2 and D3 is going to stay out there. So which one does both? D1 is in there. So R1, R2, and R3, as well as D1, support the farm bill. D1 and D2 and R3 support the budget. And then this guy does not support neither one of them. How does that look?
It looks
Kind
right
of hard
here.
to see both.
So they are not mutually exclusive, right?
Yeah, these are not mutually exclusive because D1 and R3 support both. R1 and R2 are just supporting the farm bill, and D2 is just supporting the farm budget, and that's a nothing. Neither one. For a school field trip, the students had 2 options for lunch: a turkey or egg salad sandwich. So it is impossible for a student to have both lunches. So turkey or egg salad. If the probability that a student chooses a turkey sandwich is 0.1 and the probability that a student chooses an egg sandwich is 0.6, what is the probability that a student chooses a turkey or egg sandwich? All right, so we're told up here to have both. All right, so that's essentially meaning that probability A of egg or T and E is equal to 0, okay? They're giving us that information. So therefore, since, and we looked at that formula before, this would be it if we just use it specifically for that one. So we know that that one at the bottom is both.
First
So all
one,
we're going to do is
or,
just this
right?
out. What's that?
The first one's supposed to be or. T or E.
No, we're finding or. Oh, I'm sorry. Yeah, thanks. Yeah. Yeah, and that's the one we don't know. That's the one we're finding. So we're just going to add these up. 0.1 plus 0.67 minus 0. So it doesn't. It's n. It's 0.77. 0.67 plus. So there we go. All right, so we got a contingency table here. We're going to fill it out. All right, and generally you want to start on a row or column that's only missing one. And this one looks like a good one. So these both have to add up to 90, so we're missing an 80. If over here, the total of male and female is 45, that means we need a 14 there. 4 plus 1 is 5, and 3 plus 1 is 4. Now we can go along the rowway. 31, I think that's 111. Let me double check it. Sometimes. Yep. Okay. And then here, 111 plus 24, 135. Now it's a good idea to just check them. So 45 and 95 indeed is 135. We'd already looked at 14 and 10 gives us 24. 31 and 80 give us 111. 80 and 10 is 90. 11 and 24 is 135. So that looks good. Any questions about it? All right, now this is the one we're going to get. You got to get the order right. Okay. Here's the key. Given that the person went to college. So remember, the symbol okay, so that line right there reads as given. So that's our hint. Okay. So C is going to be there. So that would be the probability of J given C. Is that one on there?
Yep.
That's the second one, isn't it? So it's tempting to do that, but that's not the same thing. And neither one of these are and. Whenever you see that word given in there or something that's conditional, then you're thinking about conditional probability. And is multiplication, and is and, or is or. This is given, that's conditional. All right. Given the following information, determine whether B and C are independent, mutually exclusive, or both. All right. Here's the key to mutual exclusivity here. All right. Now, if these two were equal, these are not equal. If they were, then we could say that they were independent. All right. So these are only mutually exclusive. Make sense? Anybody disagree? Are we all right?
Wait, say it one more time.
Okay, this one right here, these two are really the same thing. They could give you either one of these. This one or this one, they essentially mean the same thing. So if you got either one of those, that's your key that there is no intersection, that they are mutually exclusive. Okay?
Okay, got it.
Because the and is 0. It can also be done with this one. But there's no independence because this one and this one have to be the same.
Okay.
Okay? Those two right there are not equal. So there's no independence. If those two are the same, the one that appears first there and this one on your conditional and this and the B, the single event, then that means they're independent. That's the nature of independence. Let's look at that over here. This thing always goes back. And that's the same thing. That's what we got over here in my notes. Here's somewhere. There we are. See these here? That's the thing. You can have it either way. If the probability A given B is equal to A, probability of A, then it's independent. If the probability of B given A is equal to probability of B, then it's independent. Notice that on this one, neither one of those are the case. These two are not equal. So therefore, no independence. So, given the probability of a company having a newspaper in the having a section in the newspaper, a company having a section in the newspaper is 0.43. So the given is right here. So that's the whole thing, probability. So let me write the formula out. It's the same thing as the and. It's just arranged differently. So I'm going to use N for the newspaper and W. So that's what we're doing. So we've got this side. That's what this is. So this is the 0.84. And then we got the denominator here, which is the company having the newspaper. And then what we don't know is up here, I'm just going to stick an X up there so we don't have to keep rewriting that thing. And then we just know that it's the probability of both. So this is pretty easy to do with this one. All we're going to do is just do that cross thing. And that means then X times 1 is just 1X. So it's 0.84 times and that's going to be what? 0.84 times 0.43. Three decimal places. We can knock off that 2. Oh, this is
Wait.
just a basic.
I got
What's up?
I got 361. 0.84 times.
Oh, maybe I wrote it down wrong. Yeah, I did. That's why I like to copy and paste if I can. There we go. Thanks. All right, so this is just the probability of finding a 6. There's 4 6s out of 52, and both are divisible by 4. So 1 out of each suit of 13 is a 6. All right, not B7. All right. There are, I think there's 3 7s. Let's go over and just look real quick. It helps to look at the sample space sometimes. All right. So these right here are the numbers, okay, on each die. Okay. So there's 1. Oh, it said 7, right?
Yeah.
So there's 1, 2, 3, 4, 5, and 6. And that's the one that appears the most. I don't know much about how craps works, but that's the number that appears the most. And I think generally that's bad, but 1, 2, 3, 4, 5, 6. But they're not asking us all that. Will not be 7, so the probability of 7 is equal to 6 over 36, 1/6. 1, 2, 3, 4, 5, 6. Right. Okay. So therefore, we got to find the probability of not 6 by using the complement rule. Not 7, I mean. So that's 5/6. 1 from 6 gives us 5, and we keep the same denominator. You could also do 30 over 36, and then it would simplify down to that. All right. So looks like this is another out of 62 adults, 22 prefer red wine, 39 prefer white wine, and 9 prefer both red and white wine. Find the probability of choosing an adult. That's supposed to be and, not and. An adult who prefers red wine or white wine. So we're using that same formula. All right, so let's see if we can figure this out. So red or white is what we're trying to find out. So the probability of red, 22 over 62. I'm just going to keep the big denominator for now because we're adding. The white is 39 over 62. And then 9 prefer both. Let's see here. Does that look good? So the probability of red wine people is 22 over 62. The white wine is 39 over 62. And then the both is 9 over 62. And then 30 plus 22 is 52 because the 9 is taking out that 9. And so we're going to just, we're going to do it as a decimal. So and 4 decimal places. And it looks like that's spot on. We don't have to change anything. All right, any questions? All right, let's see. What is the probability of drawing a 10 and then drawing a jack from a standard deck of cards if you don't replace? And all right, and then if we don't replace, that's a conditional probability. In other words, the probability for the second pick is going to change. All right. So all right. So both of these are the same probability to start out. So there's 4 out of the 52 are 10s. Now, once we pull the 10 out, there are no longer 4 10s in there. There's 3 10s in there, but that doesn't matter for this one because we're picking jacks next. But one's missing. And it's the 10. So we still got 4 jacks in there. Now, as I said, if we simplify this down first, it'll make the math easier. Because then we won't have to simplify it so much. $663. And this seems familiar. All right, how does that look? Any questions about that one? So there's 4 10s in the deck of 52. We take that 10 out. There's now 51 in the deck. And we didn't touch jacks the first time, so there's still 4 in there. This simplifies down to 1/13, makes the math a little bit easier to do. And then no simplification in this case. All right. All right. The Transportation Committee polled a sample of students, asking them to state their most common mode of transportation. The results showed that 41 students drive cars, 52 students walk, and 23 students ride a bike. All right, what is the probability that a student drives or walks? Okay, first of all, we need to know how many there are total. So what in the world is 41? So 116? All right. So that's our denominator for all of them to start. So we want to find what is the probability that a student walks or drives. So it sounds to me like we're going to just have to use the old formula. So walk or drive is equal to the probability of walk plus the probability of drive minus the probability of both. All right, so let's see what we got here. So 41 students drive. $52 students walk, and we're putting them over the total of all. Minus. Oh, wait a second. They don't have any of this. This is 0. These are mutually exclusive. Because there's 3 different things: drive, walk, and bike. But we're only worried about drive
Do
and
we
walk.
take out the bike though?
No, because
Okay.
they're still in there,
Okay.
because that's part of your 116. So there's only a certain proportion of them that are walk or drive.
Gotcha.
So 5 and 9, so this would be 93. And we want to see if we can simplify it. I know that simplifying the fractions can be a pain in the neck. For the most part, that they've been very forgiving about it. But I feel like I should try to give you a couple of hints. If they end in 0 or 5, they're divisible by 5, of course. If it's ending in 0, then it's divisible by 10. If it's even, then it's divisible at least by 2. It could be more. It could be 4 or another number. But the one that's most useful for me is if the sum of the digits add up to a number that's divisible by 3, then the whole number is divisible by 3. See, like for instance, 9, 10, 11, 12, that's divisible by 3. But let's see this one: 6, 7, and 8. That one's not divisible by 3. So I don't think there's anything we can do. I like to at least check on those. I don't think we lose anything, but it does help to be able to simplify them. A hospital wants to determine if a new brand of tests is affecting and detecting whether or not a patient has strep throat. So another complete the 10-digit table. All right, so this is pretty easy. This is one of my favorite things to do. All right, so you can pick any one that's got a one that's missing. Let's do that row. So 302 from 332 would give us 32, right? Let's double check it. 302 plus 32, 334. Here, the 61 from the 68, because the 668 is the total. So this is going to be 7 at the end there. So this is 607, I believe. Let's double check it. Good. And now the only thing we can do now is go row wise. And I'm going to do this one first, since those were already there. $668 minus 334. So that's also 334. And then going down here, the 360. Ooh. Something's not right, is it? We didn't put that in.
668 plus
Oh, I
3.
didn't add them up. I subtracted. What the world? Yeah, this is the total, so I got to add them. There we go. 1002. There we go. That's 1002. All right, and so now minus the 363, 639. Now I'm going to spot check the ones that I had already done. The ones I had to do. So 332, let's see, 32 and 607, 2 and 7 is 9, 3 gives us 3, and then that's right. 302 and 32, so 2 and 2 is 4, 0 and 3 is 3, and then that's another 0 there at the beginning. 607, 621, so this one looks good. Okay on that?
Yep.
Oh, another one of these filling in. A college distributed a survey asking students their favorite pet, cat, dog, or bird. So we just got to do the contingency table. I thought maybe they might have us answering a question about it, but they don't. So we just fill it in. So I'm going to add those two up since that's just one. So that means 19 goes here. And then we're going to take away the 43. So 132. All right, let's see. And I'm going to add up going across. Let's see if these come out right. So that's right. 82. Oh, what did we do? Oh, I didn't put in the whole middle number. 235, that's good. Okay, so good.
Wait, I got 218 for the dog.
For which one?
Under the dog.
Here?
Yeah, 43 plus 175. I mean, yeah, right?
Well, it's got to be less than,
Hold on. Oh, I did minus.
So-
Hold on.
175
You're right.
minus
You're right. No more.
132, 43. Okay. All right. So assume there are 24 students in a music class, and 18 of them feel comfortable sight reading music. I'm trying to go to slow because I wanted to just, make this a event to go everything, but at this rate, I might go through all of them. I don't know what we'll do next hour. All right. Assume there are 24 students in a music class and 18 of them feel comfortable sight reading music. Of the 18 who feel comfortable sight reading music, 15 play piano. Find the probability of choosing a student who feels comfortable sight reading, and play the piano. Given, here's a key, given that the student is comfortable sights reading music. All right. So there are 24 students. All right. So this is a conditional probability. Find the probability of student who feels comfortable sight reading music and play the piano. So we're using that same one. All right. So it works like this. So this is piano, given they feel comfortable sight reading. All right. So we've got so this should be the probability of both. And then this is the probability of S. So let's fill in the ones we got. All right. So we got I think we can just do this with the numbers. So this is the one we don't know up here. So we know this one. $18 over 24. We could probably just get away with putting 18 and do it like that, but I want to. And this is what we don't know. And then this is equal to, because they give us this one. Of the 18 who feel comfortable reading, 15 play the piano. All right. So we can let me try something real quick. No, that's not good. I was trying to see if there's like an easier way to go about this. All right.
So wouldn't it be, there's another one where it's like,
There's probably an easier way to
Probability.
do it if I had just done it like
Yeah.
actually,
probability of
what?
A and B equals
Probably if I did
probability
this
of
would be
A given
easier.
B. Okay.
Just solve it for the and.
Yeah.
Piano and S is equal to the probability of piano times the probability of P, P given S. I'll make those small so we don't mix it up with the probability. All right. So this one we know. Here we know piano was 15. $18 of them feel comfortable sight reading music.
Is the given like
This would be where
the
the
A
given's
given
going to go.
B, is that a division problem? You know what I'm saying?
No, we should assume we should be
No?
able to do it here. So It's in there 24/7. So the probability of piano given sight reading is equal to 15 over 24. Right?
I put 15 over 18 because it's out of the 18,
The
right?
ones who are sight reading. Oh, yeah. Thank you. Yeah, thank you. Because this is the conditional one. All right. And then this one, for the probability of piano, how many of them play the piano total?
That's the 15 out of 18, right?
15.
Yeah, I mean,
Did it a whole different way. I must have not did it right.
so I think that's it. So let's simplify them. Both of these are divisible by 3, so 5 eighths. So 15 is divisible by 3 5 times. 24 is divisible by 8 times. This is divisible by 3 5 times. And 6. And nothing to simplify, but they want it in decimal. We're getting close to the end. I can tell my brain is starting to gel out here. So 4 decimals. All right. Maybe in the next hour we can come back and look at the ones like this and see if we can understand them a little bit better.
Because
Because
the given is the sight read and music, which is 18 out of 24. The piano is 15 out of 18. The 15 play piano of the 18 that
Okay, but it's 18 who a sight reading. Okay, of the 18 who feel comfortable sight reading, that's the given. That's the 18 down here. 15 play piano.
So you wouldn't subtract the
Given
15 from the 18, and then you would get the 3 students that do feel comfortable with both.
well, those 3 that I mean, they're giving us the 18. The 18 are the ones who feel comfortable sight reading.
Correct.
And that's what we're looking for. That's our given. So that's our 18.
But you want the sights reading and play the piano.
But that's what we're doing by multiplying these two up here. See?
Okay, I did it a
This
whole
is the
different way.
probability of just the piano. Okay, because it was find the probability of students feels comfortable sight reading, given and plays piano, given. So here's the and. So we find that by the probability of piano times the probability of piano given that they're sight reading.
Okay, yeah.
Uh,
yeah, we're gonna have to come back to this one.
yeah, let's come back to it because I thought I was going to be able to finish today for a little bit. Oh, and this is that crazy odds ratio. Well, we'll just start here when we get back. And then we come back and look at them. I guess I could go ahead and submit it and I get to do it again, right? And I can see the ones I got wrong.
Yeah, you
If
should
I
do.
got one wrong. So I think there's 26 of them. Oh, we can answer this one real quick. Of the 50 runners in a race, we want to know how many different ways runners can finish. That's permutation. because order matters. How many different ways runners could come in? To solve this problem, we want to list runners so order will matter. All right, so this is all right, we'll get that one afterwards. What we'll do is I'll finish up at the beginning and then I'll submit it. And if we got any wrong, I'll come back and we'll make sure. All right. Because I feel pretty confident that I can get, 90%, but that one is bothering me. Plus, there's always a few where I forgot to do this or that. I guess I'm going to have to submit it now, though, because if I don't submit it, when I come in to do the thing, it's going to. So we stopped doing which one?
It didn't say if it was timed.
20.
Stopped on 20.
I think
yeah.
it's 2 hours. I might have forgotten to put it in, but.
Yeah, I don't think I seen any time. That's why I was like, oh, go
Yeah.
ahead and start it.
Well,
while
the
we're-
problem is, though, because I'm as a student, I can't start up the Zoom in 120 as a student. I got to do it as a teacher. So I got to get out of this view.
Oh, well, I hope it's not time because I just opened it to kind of look at it and then asked it out.
I don't
Well,
see
you
any.
can do it again.
I don't see any. And it's not like counting down.
It
next
might not be.
to-
I can't remember if that was something that they filled in automatically because there's some things that are a default. Well, we'll check back in a few minutes and see. So
All
get a
right,
little
sounds
break.
good.
I'll see you in a minute.
Thank you.
Thank you. See you in a bit, Professor Cruz.
Bye bye.
Bye-bye.